Okay, so in this section, we're going to be looking at what are called binomial random variables as well as geometric random variables. And the first thing you're going to need to do is to be able to determine whether it is a binomial random variable. So to be able to do that, you're going to use what's called the bins method. And so when you're using the bins method, this is your way to check and see, does this fit as a binomial random variable? So the first thing you're looking for is your B, which is that it's binary. And by binary, we mean basically that the outcome is either a success or a failure. Now you could have multiple things that could make it a failure, or just one thing. Like for example, it could be flipping a coin, and success would equal getting a heads. Well, then tails is a failure. It could also be rolling a six-sided die, where success is rolling a 3, and a failure would be a 1, 2, 4, 5, 6. Okay? But the binary part is just that the outcome is either a success or a failure. The next thing you're going to be looking for is independence. Okay, and so you're going to be looking to see, are those trials that you're doing independent? And remember, our independence is that the one trial does not affect the other. Okay, not cause and effect, just that one trial does not affect the outcome of the following trial. Okay, the next one that you're going to be looking for is our number of trials. So when you're doing a binomial random variable problem, there is going to be a set number of trials in advance. I'm going to flip a coin 10 times. I'm going to roll a die 50 times. This couple is going to have 3 children. So there's already a set number of trials. It's fixed in advance. And then the last thing you're looking for is success. And by success, we mean the probability that you're going to get success. For example, if I'm flipping a coin, the probability that I will get a heads, which was our success. If I'm rolling the die, the probability that I will get a 3, which is a success. So our success is the probability, and it has to be the same probability for every trial. So the same probability that I could roll a 3 every time, the same probability that I could get a heads every single time. And so if your variable meets these 4 conditions, then we have a binomial random variable. And in your binomial random variable setting, x is going to be equal to the number of successes that you have. How many times you flipped a head, how many times you rolled a 3. Okay, so x is going to be equal to your number of successes. So when we look at the distribution for a binomial random variable, we're looking at the probability distribution. Okay, so that's all that is the likelihood that I'm going to get however many of successes that I'm looking for. And it's going to have certain parameters on it. And the parameters are going to be defined as n, which is going to be our number of trials. Remember, that's set ahead of time. That's one of the conditions of it being a binomial. And the parameter p, which is our probability, which is our likelihood of success, right? Our probability of success on any one trial. Which means, again and again, that probability has to be the same every time, every trial that we do. So those are our parameters there. And x also is going to be a whole number. So x will be a whole number. I can get this success a certain amount of times from 0 to n. Bit n being our number of trials. So I could either get a success 0 times, every single time, or any of the times in between. Okay, so let's look at 3 quick examples here to determine whether these are binomial random variables or not. So the first one here is genetics says that children receive genes from each of their parents independently. Each child of a particular set of parents has a probability of 0.25 of having blood type O. Suppose these parents have 5 children. Let's x equal the number of type O blood. Okay, so remember, the way we determine if it's a binomial variable is that we need to do the bins method, right? We need to determine if it is binary. So is there a success and a failure? Yes. In this particular case, success is that they have type O blood, where a failure would be any other blood type. So meets the Ben's criteria for it meets the B. Independence. Does the outcome of the blood type of one child impact the outcome of the next child? No, it does not. So these trials are independent from one another. Okay. N, do they have a set number of trials? Yes, they're going to have 5 children. So there's a set number of trials there. And then S is our success. Do they have the same probability for each child to have type O blood? Yes, it does at 0.25. So this one meets our Ben's criteria, so it would be considered a binomial random variable. So looking at our second one, we've got a deck of cards. Turn over the first 10 cards one at a time. Y equals the number of aces that we observe. Okay, so do we have a B, a success and a failure? Okay, yes we do. An ace is a success. Okay, anything else would be a failure. Is each one independent of the next? So does the one trial affect the next one? They do. Okay, remember, I'm not returning. In this particular example, I turned over the first 10 cards. I didn't return them. So they are not all going to have, yes, I have 10 cards that I'm looking at, but they do not all have the same probability of drawing an ace. Okay, and since they all, because I change every time I turn over a card, since I don't return it, I change that probability. You know, I become a 4 out of 52, and then if I didn't draw one, that becomes a 4 out of 51. Okay, so my probability is not the same each time. So this one is not a binomial random variable. The last one, I've got a deck of cards again. Okay, I'm turning over the top card and I'm putting it back and I'm shuffling again, and I repeat this process until I get an ace, and W equals the number of cards required. Okay, so again, I have a success and a failure, an ace or a not. They are independent of one another because I am returning them, so my probability is the same. However, I do not have a set number of trials. I am working and I'm drawing a card until I get an ace. I am not counting the successes. I am counting how many cards I have to turn over until I get a success, and that's our geometric kind. So that would not be a binomial. Okay, so running through the check your understanding examples here. So for these, I've got students at, I'm sorry, I skipped one. Okay, so shuffle a deck of cards, turn over the top card, put the card back in the deck, and shuffle again. Repeat the process 10 times. Let X equal the number of aces that I observe. Okay, so again, I need to determine my Ben's criteria. I do have a success failure, right? The number of aces, so that's a success if it's an ace. I am putting the card back in the deck, so each trial will be independent, and I have the same probability of drawing an ace every time. It's 4 out of 52. That doesn't change. And I'm repeating the process 10 times, so I have a set number of times I'm repeating it. So this would fit the Ben's criteria, which would be my justification, and it would so it would be a binomial. Okay, choose number 2. I'm choosing random students from the class. Okay, Y equals the number who are over 6 feet tall. Okay, well, again, I'm testing my Ben's criteria. I have a success versus a failure. Okay, but they're not independent. I'm not going to have the same probability every single time. Okay, I'm not going to have, because I'm not doing replacement, right? I'm pulling students at random, but they're not going back into the pool every time I pull. Okay, and so my next one, I'm rolling a die, and I'm rolling it 100 times. So I have a set number of trials. Sometime during the 100 rolls, okay, and I have a set number of trials. Okay, sometime during the 100 rolls, one corner of the die chips. W is the number of fives that I roll. So I have a success failure, which is the number of fives. The problem I have is when that die chips, that probably changes my probabilities, and it doesn't make them necessarily 1 out of 6, because as the die rolls around on the table, the chip could affect the way it falls. So this one would not be a binomial either. Okay, so let's look at some examples now then of using binomial probabilities and calculating binomial probabilities. So we're going to be working with this example of this family. So each child of a particular set of parents has a probability of 0.25 of having type O blood. Genetics say that children receive genes from each of their parents independently. If these parents have 5 children, the count X of children with type O blood is a binomial random variable with my number of trials, n equaling 5. My probability is 0.25 of success on each trial. So that's the n and the s of my bins. It said it was independent, which was the I, and I have a success or a failure, which is type O blood or any other type. So it's a binomial probability. So let's look at the example here of the probability of x equals 0. Okay? So if I want to find the probability of x equals 0, that means I'm looking for the probability that none of the children have type O blood, so that I get a failure every single child. Okay? So the easiest thing to do here would be to use my complement rule to find out what the probability of a failure is, right? If I know the probability of a success is 0.25, then I know that the probability of a failure is 1 minus 0.25. So my probability of not having type O blood is 0.75. If I want the probability that none of the kids, x equals 0, remember x is my number of successes that I have, so x equals 0 means I want the probability that the first kid was a failure at type O blood, the second, the third, the fourth, the fifth. All 5 kids failed for type O blood, okay, which would give me 0.75, which is my probability of the failure, right, to the 4th power. Okay, I'm sorry, to the 5th power. I'm a step ahead of myself here. So 0.75 to the 5th power, right? Probability of the failure times the failure times the failure, you get to the end. Okay, which would give me a probability of 0.2373, that none of the children are going to have type O blood. Okay, well now, what if I wanted to find the probability of x equals 1? So let's use our clean slate now to work on this. So again, we're working on the probability that x equals 1. What we need to keep in mind here is that there's a lot of different ways we could have x equal 1. It doesn't say that it has to be the first child or the second or the third. It just says that there's one success out of the 5 children. Okay, so we could find the probability of a success, failure, 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 okay, which would be a success is 0.25, followed by 4 failures, which would be 0.75 to the 4th power, right? And so I can figure out what that is, okay? And then what I need to keep in mind, though, is that I also have to consider that this could be the failure, the success, that could be the success, the 4th one could be the success, or the 5th one could be the success. So basically, I have 5 ways to meet the criteria of P, the probability of x equals 1. I have 5 different ways to do that. So my answer is not going to be just this. It's going to be 5 times 0.25 times 0.75 to the 4th power, which is going to give me a probability of 0.39551, right? I need to add up the probabilities that it's the first kid that's a success, plus the probability that it's the second kid, plus the probability that it's the third, plus it's the 4th, plus it's the 5th. All of those probability values are calculated by 0.25 times 0.75 to the 4th, so I can just multiply that out by 5. So that tells me they have about a 39% chance, okay, of having one success, exactly one kid that has type O blood. Okay, not at least one, but one kid with type O blood. So there's a formula to calculate this, okay, when we want to know that the probability. So when we want to know the probability that x equals what we call k. And k is our exact number of successes in a trial. Okay, so this is successes. So when I want to know the probability of x equals k, so in the last example it was 1, right? 1 success. So that's my probability of exactly k number of successes in n number of trials. So when I want to know that probability, I need to take the number of arrangements times the this formula is crazy. Okay, so it's my number of arrangements. So how many different ways can I get that? For example, in our last one, it was 5 different ways that I could get 1 success. Okay, times the probability of k, which is how many successes I had, times 1 minus the probability of n minus k, okay, which equals this kind of crazy, extra crazy looking formula. Probably not as much for you guys because you've been taking math more recently than I have. So n over k, you'll notice that this is not a fraction. There is no line between the n and the k. This is not a fraction. Okay, times pk times 1 minus p times n to the minus k. Okay, so what this is the n over k part is what we call our binomial coefficient. Okay, so let me change the color so you can see it better. So this part right here is my binomial coefficient. And what that means, okay, is that I have k number of successes. So I have 1 success, 2 success, 4, however many, k number of successes in n number of trials. For example, in the last one that we just did, we had 5 trials, okay, and we were looking for 1 success. So that would be my binomial coefficient. Okay, and when I write this out in factorial notation, right? So let me close some of this out for you so that you can see it better. So when I write this binomial out, okay, what that is equal to is factorial notation, which can get kind of out of control, especially if we have a big number. It can get a little crazy. Okay, so for those of y'all that don't remember or haven't seen in a while, right, factorial notation looks like this: n times n minus 1 times n minus 2, okay, times n minus 3, all the way down, okay, where as well factorial for 0 equals 1. Okay, so a lot of this stuff would end up canceling out. Like, let's look at an example here. So an example, I want 2 successes in my family of 5 here, right? So I'm looking for 5, 2, and this is my binomial coefficient here. So what this becomes is 5 over the factorial of 2 and 3, right? 2 being k, right? I wanted 2 successes. 3 being n minus k, right? 5 minus 2. Okay, so let's erase some stuff and see what this is going to look like here. So when I set this up, again, the factorial of k times the factorial of n minus k. So when I set this up, basically what this looks like is 5 times 4 times 3 times 2 times 1, right? That would be 5 times 5 minus 1 times 5 minus 2, etc. Okay, over 2 times 2 minus 1, which is just 1. Now times 3 times 3 minus 1, which is 2, times 3 minus 2, which is 1. Okay, and so I get a lot of stuff that cancels out, which is great. Okay, so I get a lot of stuff that cancels out, and I end up with 20 over 2 or 10. What that tells me is that there are 10 ways to get a success of 2. So there are 10 different ways basically to rearrange these 5 children so that 2 of them have type O blood. The first and the second, the first and the third, the first and the fourth, the first and the fifth, the second and third, second and fourth, second and fifth, third and fourth, third and fifth, fourth and fifth. Okay, that should have been 10 successes there. But it keeps you from having to write that out, from having to figure that out. It makes sure that you're going to have the right number of successes. You are totally welcome to do this by hand. You can also do this on your calculator. Okay, and so I would definitely consider doing this on my calculator. So when you do this on your calculator, you're going to type in, so on your regular screen, like where you do computations on your calculator, you would type in the number 5, and then you would push the math button. So I type in the number 5. So I type 5, and then I push the math button. Okay, and on the math button, you're going to arrow over to prob. It should be the third, I think it's the third one. So you'll arrow over to prob, and then from there, you're going to go, you'll scroll down, and I would walk through and do this once as we're talking about this. You'll scroll down to NCR, okay, and then once you push NCR, so you push that, okay, and then you will type in your K value, and you will hit enter, and it will spit out the number 10 for you. Okay, and again, I will show you how to do this in class. We will work with your calculator if you need to. Also, in your book, it shows you pictures of that on page 392. Okay, so I'm just going to walk you through this problem. I'm not going to spend the time to write all the work down because you have this in your book. This is on page 393. So I've got the same family again. Okay, part A here wants me to find the probability that exactly 3 of the children have type O blood. So if I'm looking for that, so here's our solution right here. Okay, we've got probability that x equals 3. Okay, here's my binomial coefficient, 5 over 3. When I put that into the calculator, or you can do it all out on the, by hand in the factorial, I'm going to get 10. Okay, I multiply in my formula. Okay, so in my formula, it is my number of arrangements, which is this binomial coefficient here, or 10, multiplied by my probability to the k, so however many successes I'm looking for, so 0.25 to the third power, multiplied by 1 minus, so my failures there, to the second power, which is because of n minus k. So when I plug all that in, I get the 0.08789, okay, which tells me I have about a 9% chance that exactly 3 of the children are going to have type O blood. Okay, part B wants to know if the parents will be surprised if more than 3 of their children have type O blood. So what I'm looking for here in part B is the probability that x is greater than 3. So the probability of x being greater than 3 is the same as the probability that I have 4 kids that have type O blood and that I have 5 kids that have type O blood. So I get my binomial coefficient, 5 over 4. Again, plug it into my problem, basically my successes to the 4th power, because in that first instance k is 4, okay, times my failures to the n minus k, which is 1. And then the second part, the probability that 5 out of 5, my binomial coefficient, which should only be 1. There's only one way that I can get all 5 kids to have type O blood, times my success to the 5th power, okay, to the k, and then in minus k here, which is going to be equal to 0. So, because 5 minus 5, to my failures to the 0 power, which gives me 1. So when I add those two probabilities together, I get a probability of 0.01563. So basically about a 1.5% chance that more than 3 children are going to have type O blood. Okay? And so that would most likely be considered surprising. Okay, so here's the part I know you've been waiting for, how to do this on your calculator. Okay, so on your calculator, there are 2 commands that you will need to choose from, and you will need to choose correctly. If you choose the wrong one, you will get 2 different values. Okay, so you have the binom PDF and CDF here. Okay, and so what you need to determine is whether you're looking for a probability that X equals an exact number of successes, or the probability that X is less than or equal to a certain number of successes. Kind of like your z-scores and stuff. Remember when we calculate all those z-scores, it only shows what's to the left, and I have to do like 1 minus to find the probability of it being greater than. Same thing here. The binomial CDF function will only compute the probability that X is less than or equal to K. So you may have to find that and then manipulate into what you want. Okay, so when you're doing this on your calculator, okay, it's second bars, distribution, so it's that distribution button. Binomial PDF and binomial CDF are way near the bottom. It's a little bit faster actually to hit the up arrow and go up through the list instead of scrolling all the way down. Okay, when you type this in, you're going to need to, again, remember our showing our work. When you go to show your work, remember you can't just show this, you're going to have to identify it. So showing your work here is going to be binom, PDF or CDF, and then trials are equal to whatever they are equal to. Okay, the probability is equal to whatever it is equal to, and X value, not just X value is equal. Okay, it's right there. Okay, so when you type all of those in and then you hit enter, you will get your probability for this. Okay, so looking down here at part B, should the parents be surprised if more than, so the question in this case was, were more than 3 of their children having type O blood? To find X being greater than 3, I'm going to have to use my complement rule, right? 1 minus the probability that X is less than or equal to 3. Here's where it gets a little bit tricky. And one of the tips that I've seen that I think could be helpful to determine whether you would include that 3 or not, right, is to list out my possible values of X, right, which are 1, 2, 3, 4, and 5. I could have 1 success, 2 success, 3, 4, or 5 successes. And I want to find the probability that X is greater than 3, which means I want the probability of 4 and 5, which means I would include, because I do not want those probabilities, I would include 3, okay, which is why I'm going to set my X equal to 3 when I type it into the calculator, okay, as opposed to X being equal to 2 or being equal to 4. Okay, so when I'm doing something, when I need the less than or equal to, I'm going to use the binomial CDF function. Okay, so same as before, I'm going to run through this real quick since this is already in your book and laid out for you. It's on page 396, and I'll write out how to do the check your understandings for you. So fast food restaurant, running a draw 3, get it free lunch. So customer orders, excuse me, a touchscreen display shows the message, press here to win a free lunch. Computer program simulates 1 card being drawn from a standard deck. If the chosen card is a 3, a customer's order is free. Otherwise, the customer must pay the bill. So it's a 2-part problem here. All 12 players on a school's basketball team place individual orders at the restaurant. What's the probability exactly 2 of them win a free lunch? And then part B says if 250 customers place lunch orders on the first day of the promotion, what's the probability that fewer than 10 win a free lunch? So same as we did with normal problems, this should be a 3-step process for you. You state your distribution and your values of interest. So in part A here, okay, X is my number of players who win a free lunch. All right, that's my value of interest here. I have 12 independent trials of the chance process, each with a success probability of 4 out of 52. And so it's a binomial distribution with n equals 12, probability equals 4 out of 52, and I want to find P, the probability of X equaling 2. That's my distribution. Okay, so my distribution, my trials, okay, the fact that it's independent, my value of interest. Then I'm going to perform my calculations. Okay, I could do one of two things. I could use my probability formula. Remember, here's my binomial coefficient, which tells me that I have 12 trials and I want 2 successes. Okay, and then I can plug all that information in to my formula. Or, again, I need to type all of this out. I need to write all of that out. When I'm doing it, my trials are 12. This is my probability, X value of 2. And it gives me a probability of 0.1754. Now I'm going to go back and I'm going to actually answer the questions. These are the same 3 steps we had when we did solving normal problems in the transforming data, right? State my distribution, my values of interest, show my work, perform my calculations, and then answer the question. So what this tells me is there's a 17.5% probability that exactly is important. 2 players will win a free lunch. Okay, part B wants to know that if I have 250 customers on the first day of the promotion, what's the probability that fewer than 10 are going to win a free lunch? So in this case, okay, Y is my number of customers who win a free lunch. I've got 200, so stating my distributions, okay, and my values of interest here. I've got 250 independent trials, chance process, success probability 4 out of 52. So it's a binomial distribution, so not a normal distribution. That's stating my distribution. It's a binomial distribution with n equals 250, p equals 4 out of 52, and this is what I want to find. This is my value of interest. I need to show my work. Okay, so I want to find that y is less than 10. I know most of you are going to want to plug this into your calculator. Okay, I do. I don't want to try to do that factorial notation and stuff. So if I'm going to plug this into my calculator, though, I need to be sure whether my x value is set at 9 or my x value is set at 10. Okay, and I want less than 10, which means I'm not including 10, 11, 12, all the way up to 250 in that in those parameters. I want 0 to 9 people winning a free lunch. So when I type in, I'm using my CDF, not my PDF. Okay, my trials are 250. My probability is still 4 out of 52. My x value here is 9, which gives me a probability of only 0.6%. 0.6%. Okay, and so there is almost no chance that fewer than 10 customers will receive a free lunch. Okay, and they go on to say if that actually did happen, then the customer should question it. Okay, so let's run through the check your understanding example. So to introduce her class to binomial distributions, Mrs. Desai gives a 10-item multiple choice quiz. The catch is students must simply guess an answer, A through E. For each question, Mrs. Desai uses her computer's random number generator to produce the answer key, so that each possible answer has an equal chance to be chosen. Patty is one of the students in the class. Let X equal the number of Patty's correct guesses. Show that X is a binomial random variable. Okay, so if I want to prove that something is a binomial random variable, I need to do my bins method, right? So I need to double check that in this scenario. So is it binary? Yes, it is. They either got the answer right or they got the answer wrong. Okay, each answer is independent of the next. It doesn't matter if the random number generator chose answer A for the first one, that doesn't affect its ability to choose answer A for the next one. There is a set number of trials because there are 10 questions, so there are 10 trials. And then the probability is the same for a success for each one. She has a 20% chance for success on each one, a 1 out of 5 chance on each one. Okay, so part 2 wants us to find here the probability that x is equal to 3. So, and then explain what that means. So the probability of x being equal to 3, okay, if I plug that into my calculator, okay, I'm going to use the PDF function because it's an exact thing. It's equal to 3. I need to show all my work. Okay, let me see if I can erase this other stuff. Oh, it's going to erase it all. Okay, so I'm using the PDF function because it's the probability of x equals 3. Okay, and so when I write out my work here, my trials are 10. My probability is 0.2. And my x value, again I have to write x value, not just x, is 3. And then close my parentheses. And so what that will spit out is that the probability of x equals 0.201. But then I need to put it in context. I need to explain what it means. So what that means is there's about a 20% chance that Patty would get exactly, and that's important, exactly 3 out of 10 correct. Okay, so now the question is that to get a passing score on the quiz, a student must guess correctly at least 6 times. Okay, so they need at least 6 times. Would you be surprised if Patty earned a passing score? And compute an appropriate probability that supports our answer for that. Well, something that would help support our answer for that is the probability of her getting a passing score, which means she has to get greater than or equal to 6 of them correct. Well, remember, we're doing this in our calculator and stuff. We use that binomial CDF function. It gives us the probability that x is less than or equal to however many successes we're looking at. So my probability of getting greater than or equal to 6 is going to be the same as my probability of 1 minus x is less than or equal to 5. Okay, so I can plug that into my calculator now. I can find my binomial CDF because it's a less than or equal to situation. Okay, and my trials are still 10. My probability is still 0.2. But this time my x value is 5. Okay, because remember it shows me less than or equal to 5. Which gives me a probability of 0.994. So when I plug this into the probability that x is greater than or equal to 6, which is equal to 1 minus 0.994, I get 0.006, which basically gives me an almost 0% chance. Okay, it gives me a 0.64% chance that a student would be able to pass, would get 6 or more correct. So that would be very surprising if a student was able to pass. So when we're looking at binomial distributions, we also need to be able to calculate mean as well as standard deviation of these. Okay? When we're calculating mean and standard deviation of binomial distributions, it's actually a little bit easier. So those formulas, remember, for a random variable, our formula for mean was our values of x all times our probabilities for those values, and we add all those together. Okay, but that's for a binomial distribution, and for a binomial distribution only, that will simplify to our mean of x equals our number of trials times the probability. Okay, so remember, n is number of trials, p is the probability. Okay, our standard deviation formula, remember our information about spread is about our, we have to get our variance, right? And then we need to find the standard deviation, we need to take the square root of our variance. Well, our variance in normal distributions, it simplifies down to, instead of, remember before the formula was the data point, right, here we go. So it's our sorry, a mess. Okay, it was, remember, it's the data point times the mean of x squared times the probability that actually will happen, right? And we sum all those up. Well, again, it simplifies down for a binomial distribution only. The variance simplifies down to the number of trials times the probability times 1 minus the probability. So again, number of trials, probability times 1 minus the probability. So basically our successes, number of trials times successes times the probability of a success times the probability of a failure. So number of trials times probability of a success times probability of a failure. So then when I go to find the standard deviation for this, it's just the square root of n times p times 1 minus p. So much simpler if it's a binomial distribution than if it's one of the ones that we looked at before. So let's look at a couple of examples. Okay, so this one is on page 399 in your book. So I've got Mr. Bullard's AP Stats class. They had 21 students. They assumed the students in his class could not tell tap water from bottled water. Each one is basically guessing with a 1/3 chance of being correct. X is my number of students who correctly identify the cup containing the different kind of water. Explain why X is a binomial variable. Find the mean and standard deviation and interpret. Out of the 21 in the class, 13 made correct identifications. Are you convinced that they can tell tap water from bottled water? So let's look at part A and B first. Okay, so again, I need to meet the Bin's criteria to prove that it's a binomial random variable. So I have success versus failure, correct identification versus incorrect. One student shouldn't impact the next student, shouldn't tell us anything else about the next student. I had 21 trials, so I had a set number of trials, and they all had the same probability of success, a 1/3 chance. Okay. If I am calculating the mean of this, I can just use my n times p. I had 21 trials times the probability of 1/3, which gives me a mean or an expected value of 7. For standard deviation, again, I can just plug this into this formula, the square root of n times p times 1 minus p. So 21 trials, probability of success 1/3, probability of failure 2/3, multiply all that together and take the square root, and I get a standard deviation of 2.16. And so what that is going to tell me, okay, is that if I were to do this lots and lots of times with groups of 21 students, because I can only apply this to groups of 21 students. So if I did this many times with groups of 21 students, okay, then I would say that the number of correct identifications would typically be about 7. Okay, and then that my standard deviation would be 2.16. So again, I do this lots of times with groups of 21 students, then the number of correct identifications would differ from 7 by about 2.16. So when I'm doing part C here, okay, that of the 21 students in the class, 13 made correct identifications. Are you convinced that Mr. Bullard's students could tell bottled water from tap water? Let's justify my answer. So what I'm looking for here basically is the probability that x is greater than or equal to 13, okay, which is going to be the same, because remember my calculator doesn't do greater than, it's going to be the same as 1 minus the probability that x is less than or equal to 12. Okay, so I'm going to use the CDF, right? So binomial CDF, and I put in the trials, which is 21, right? My probability, which is 1/3, and then my x value, which is 12. Okay, and when I compute that out, I get a probability of, it's like 0.9932. Okay, and so, yeah, 0.9932. So when I subtract that from 1, when I plug that in up here, and I get the probability of x being greater than or equal to 13 is equal to 1 minus 0.9932, I get a probability of 0.0068, which tells me that there's a less than 1% chance of so many of them getting it right if they were all guessing, which is pretty strong evidence that they could actually tell the difference. Okay, so back to our special quiz here. So finding the mean of x here and interpreting that value in context, right? Remember, it's number of trials times the probability. There were 10 trials times the probability of 0.2, which gives me 2. So in context, that tells me that the average number of correct answers is 2. Okay? When I'm finding the standard deviation of this, right? Remember, standard deviation is the square root of my variance. So when I plug that variance in, right, number of trials times the probability of success minus the probability of failure, which gives me 10 times 0.2 times 1 minus 0.2 or 0.8, which gives me 1.6. So when I take the square root of that to find the standard deviation, I get a standard deviation of 1.265, which in context tells me that if many, many, many students took the quiz, the correct number of answers would vary from 2 by about 1.265 answers. Okay, and so when I go to do part 3, which is the probability that the number of Patty's correct guesses is more than 2 standard deviations from the mean, and I need to show my method. So let's walk through with what we're doing here. So what I want is the probability that Patty is more than 2 standard deviations from the mean. So first of all, I need to figure out what that is, right? So 2 times my standard deviation of 1.265 plus the mean. I need to figure out what the two standard deviations is, and I need to add it to the mean so I know what value I'm trying to be greater than. So now that I know that 4.53 is 2 standard deviations above the mean of 2, I want to know the probability that x is greater than, and it just said more than 2 standard deviations. It didn't say equal to. So I want to know the probability of that x is greater than 4.53, which tells me I want the probability, right, of 1 minus x is less than or equal to 4, right? Okay, 4 would be included because it's not going to fit my criteria of greater than 4.53. So I'm going to use my CDF function on my calculator. Okay, because I'm doing a less than or equal to situation. Okay, trials here again are 10, probability is 0.2, x value is less than or equal to 4, okay, which gives me a probability of 0.967. I want to know though that my probability of x is greater than 4.53, which is equal to 1 minus 0.967, which gives me 0.033. So that's my final probability. And so what that tells me is that it's not very, the probability is not very high of Patty having correct guesses of more than 2 standard deviations above the mean. Okay, let's look at the 10% condition rule. So when we're doing statistical sampling, a lot of times sampling is done without replacement, and that would technically that would change my probability, right? But if I have a huge sample size, it doesn't change my probability that much. And so one of the things you'll need to check for is what they call the 10% condition rule. So if you're taking an SRS, a simple random sample, of size n from a population of size capital N, we can use a binomial distribution to model my count of successes in my sample as long as my sample is basically less than a tenth of my population. So I think this example illustrates it really well, and it's just easier to just go through this. So you've got this airline company that's trained 25 officers, 15 males and 10 females to become captains. Only 8 captain positions are available, though. So they use a lottery system to pick them and fill the positions. Of the 8, 5 are female and 3 are male. So you're explaining why the probability that 5 female pilots are chosen in a fair lottery is explaining why the probability that 5 female pilots are chosen in a fair lottery is not the probability x equals 5. So when I calculate that out, okay, I've got my binomial distribution here, my binomial coefficient. Okay, I calculate that out and I get a probability of 0.124. Okay, my correct probability, however, is 0.106. And the reason why this doesn't work is because they're sampling without replacement. Okay, and so the first pilot has a 40% chance for being selected for a captain, has a 40% chance of being a female. Once that person is chosen, the probability that the next one will be a female is no longer 40%. Okay, it's no longer 0.4. My binomial formula, though, however, assumes that it has to stay constant at 0.4. And this will stay approximately correct, okay, if I have, if my sample is no more than 10% of the population. But in this case, I'm sampling 8 out of 25 pilots, which is almost a third of my population, which has a much bigger swing in my probability, shifts my probability more, and so that won't work. So again, as long as I'm sampling without replacement, I'm sampling less than 10% of the population, I can still use this binomial model. Okay, the last thing we're going to look at is what a geometric random variable is. So a geometric random variable counts until you get a success, which is different than a binomial, right? A binomial counted how many successes I got. A geometric counts how many times it takes for me to get a success, okay? Not how many times I had successes appear. Okay, conditions that must be met, though, the trials still have to be independent, just like they did for the binomial. Okay, and the probability for success still has to be the same. Okay, so just like it was on a binomial. So rolling the die. So if rolling the die, a binomial situation would be out of 10 rolls, how many times did I roll a 3? Where a geometric random variable would be how many rolls does it take for me to get a 3? Okay? So my random variable y is my number of trials to get my first success. Okay? My distribution for this, you know how when we do our problems we have our 3 steps. We have to the first step is identifying the distribution, normal distribution, binomial distribution, geometric distribution. So my distribution of this is that it is a geometric distribution, okay, with my parameters here being the probability of success, okay, on any given trial. So whatever my probability of success is on any given trial, it's all the same. So let's look at our formula for this and go straight into an example. So our formula for this is right here. The probability of y equals k. Remember, k is when we get a success here. Okay, and so our formula here is 1 minus the probability to the power of k minus 1 times the probability. So let's just put this in an example right here. So the lucky day game, real quick, is basically the teacher will assign them 10 homework problems, or they can decide to gamble on how many homework problems they will get, where basically she will ask a student to choose a day of the week and then have the random number generator on her calculator generate a random number which would stand for a certain day of the week, and as soon as a student gets it right, that's how many problems they have. So they could have just one problem for homework, they could have 2, 3, 4, 5, 6, 7. Okay, so part A here wants the probability that the class receives exactly 10 homework problems as a result of playing the lucky day game. So I'm on my probability that y equals 10. So my probability that y equals 10 is going to be 1 minus my probability. Well, my probability that and this was stated earlier in it, but my probability is 1 out of 7 that they are successful. Okay, and so my probability of 1 minus that, okay, is this right here, right? My 6 over 7. Okay, to the k minus 1, well, k is 10, so to the 9th power, times my probability that they get a correct pick, okay, which gives me 0.0357. So basically about a 3.5% chance that they will be assigned exactly 10 homework problems. Okay, part B wants to know my probability that y is less than 10 and interpret that value in context here. Okay, so to get my probability of y is less than 10, I need to add up my probabilities of y being 1, 2, 3, 4, all the way up to the probability of y being 9. Okay, you are so not going to write that out. Okay, we're going to look right now at how we can find that value on the calculator. So same as before, I have two commands that I can choose from on the calculator. The geometric PDF and the geometric CDF. PDF, just like I did for the binomial, is when I want an exact value. CDF is when I want a less than or equal to. Again, they're in that second bars in that distribution menu. Okay, they're down there with the binomial. Again, easier to scroll up. You'll get there a little bit faster. Okay, so when I show my work, again, here's how I'm going to show my work. Right, I've got to enter in that I have my probability. You can see it here too. My probability and my values. So when I write this out, I need to be sure to identify that this is P and that this is my X value or Y value. Okay, but make sure you identify this out, and that will give you those probabilities. Okay, instead of having to add all the +1, +2, the probability +3, etc., it pops out right there that there's about a 75% chance that they will have less than 10 problems. Okay, you also could be asked to calculate the mean expected value of a geometric random value. So when you're doing that, okay, your formula for that is just 1 over your probability of success. Okay, so my expected value of y would be 1 over p. So let's run through this, check your understanding, and we'll be all set with these. So looking here, I've got rolling a pair of fair six-sided dice until I get doubles. And t equals how many rolls is that going to take? Okay, so t is my geometric random variable, and I have to prove that. Okay, well, I can prove that for a couple of reasons. First of all, I'm counting until I get a success. Okay, so it's not a binomial there. So I'm counting until I get a success. Each roll is independent. That doesn't impact, it doesn't dictate success or failure on the next roll. And the probability of rolling doubles on each one is the same. It's a 1 out of 6. So it fits all those criteria of being a geometric random variable. If I want to find the probability that t equals 3, and then I need to interpret that in context, okay, if I'm finding the probability of t equals 3, okay, I'm finding my 1 minus, which is 5/6, okay, squared times my success. Okay, or I could plug that into my calculator. I could use the geometric function of my calculator and plug that in. But basically, I have a probability of 0.1157 that I will get a doubles on the third roll, because that's what that's asking me. Okay, is that on the third roll? If I want t equals 3, that tells me on the third roll is when I'm going to get my success, because this is a geometric variable. Number 3 here tells me that in the game of Monopoly, a player can get an out-of-jail-free card by rolling doubles within 3 turns. Find the probability this happens. Sorry, now you can't see that over there on the side. Okay, so basically what I'm looking for here is the probability that t is less than or equal to 3. So in 3 or less rolls, I will have a success. Okay, and so I can just plug that into my calculator, or I could calculate out the probability of y equals 1 plus y equals 2 plus y equals 3, okay, etc. Or I can use that geometric CDF because I want a less than or equal to, plug in my probability of 1/6, my y value is 3, and I get a 0.4213 or 42% chance that I will get a get out of jail free card. All right, we're all set.